Hello again, my friends. We are going to continue with the next module of our course. This is the sixth module, and the name of this module is load sizing heuristic. So we have approached the load sizing problem with optimal solution algorithms. We have developed an integer programming model for the load sizing problem. We have also developed a dynamic programming model, which is also named as Wagner-Witten algorithm. And we have tried to solve this problem optimally. Now, unfortunately, this is not going to be very practical, especially in the short-term inventory planning problems. At aggregate level, it may be practical, but for short-term decisions, using optimization algorithms for the load sizing problem is not a good idea. We are going to explain this in a moment. So we are going to explain the load sizing decision as an operational decision, and we will say that optimization is not a good idea for such circumstances, for short-term or operational decisions about load sizing, and we will be in need of a heuristic method to solve such a problem. And there will be some proposed load sizing heuristics in literature. Therefore, we are going to examine them one by one during this module. Okay, so we have the second and the third section here. Actually, it is a joint section. I do not want to have a long list in the right hand side of my presentation file here. So I will be explaining basic load sizing heuristics in the beginning, which are not usually very iterative. Then I will be explaining the iterative load sizing heuristics, which are a little bit more advanced and a little bit complex to understand compared to the basic load sizing heuristics here. In the end, I will explain differences between these load sizing heuristics, and I will show you a small benchmark in the performances of load sizing heuristics here. So as I have said, sometimes when you solve the load sizing problem for the aggregate level plans, you can choose optimization. However, if the load sizing decision is an operational decision, for example, if you are trying to determine the order quantities in a net requirement plan of a master materials requirement planning system, in that case, the load sizing decision becomes an operational decision. And for these operational decisions, optimization approaches are not very practical. Now, if you have a large number of discretized periods in the planning horizon, then the complexity of the linear programming model or the integer programming model, and in fact, the dynamic programming model, they will increase as well. The complexity will increase as well. So it will take a longer time to find the optimal solution using such mathematical models. And especially when you intend to optimize the load sizes for multiple inventory items simultaneously, you need to think about the dependence between these multiple inventory items, because think about a bill of material, and within a bill of material, there are several inventory items which are dependent, which should be dependent to each other when we are making inventory decisions, because I mean, there are some parent and child relationships between the items in a bill of material. And when you consider these dependencies, this means even if you try to find the optimal load sizes for a certain item, at global scale for the overall load sizing decision for all materials or all items in the bill of material, that is not going to be necessarily the optimal one. Okay. So if you try to locally optimize the load sizes for a single inventory item, which has a certain dependency within the bill of material to other items, that is not going to be an globally optimal decision for all the inventory items, unfortunately. And if you intend to develop a mathematical model such as integer programming or dynamic programming model, when you consider all items in the bill of material, that is going to be too complex and it is going to be too time consuming to solve. And another thing about the load sizing decision as an operational decision is that even if you determine the optimal load sizes for a short-term plan, we know that this short-term plan or this model will be using the demands collected from the master production schedule or any other type of production plan. And these are usually subject to change whenever a new order is introduced by any customer of ours, then we need to update our master production schedule or the production plans. And that means we need to revise our load sizing decisions every once in a while. And if we are going to revise this decision every once in a while, it is not a good idea to consume so much time for this revision, right? So there is this thing also I need to mention about this thing. I mean, even if you develop a master production schedule for a while, and you determine your load sizes based on the master production schedule. Whenever a change occurs in the master production schedule, there is some part of the master production schedule that you can never ever change. That is called the frozen period or the fixed period. However, except this part, except the frozen period, the other plans may change, and this change can also force you to revise your load sizing decisions. So why should we solve the load sizing problem optimally by consuming so much time with a complex optimization approach? So we say that instead of developing optimal solutions to the load sizing problem, the inventory managers, they usually use suboptimal solutions based on the heuristic methods, and these heuristic methods are classified as load sizing heuristics. Okay, now what is a heuristic method? Let's explain it. A heuristic method is any practical method for problem solving that is not guaranteed to be optimal, perfect, or rational, but is nevertheless sufficient for reaching a satisfactory solution in a fast manner. So by satisfactory means we mean a suboptimal solution. So with the heuristic method or with the heuristic solution approach, you will not be guaranteeing the optimal solution to the problem, but a reasonably acceptable solution to the problem, which is going to be approximately close to the or almost close to the optimal solution or the optimal objective value, but it is just going to be fast. Okay, so at operational scale or operational level, instead of using the long complex optimization procedures just to improve our solution a little bit further, we are basically trying to remain content with a suboptimal solution, which is almost close to the optimal one in the objective function, but it is also fast. So that's a good thing, I think, for operational decisions. And for the load sizing problem that we have studied in the last module, there are several heuristics proposed in the literature. Some of them are very easy to implement. Some of them are a little bit complex and require some iterative approaches, but still very easy. Okay, so the solutions that we are going to develop here are not going to require ask you to use any complex numerical methods such as integration or optimization. So we are just going to make some small calculations, and we are going to choose the best decision in the short term to end up with a satisfactory solution to the load sizing problem. And we are going to practice each of these heuristic methods one by one in this module. Now, the load sizing heuristics that we are going to mention in this module are practically used in the materials requirement planning systems. Now, we have a product structure or a concept that is called bill of material in the materials requirement planning systems. So whenever we develop a master production schedule, you feed the system with the current inventory levels of several products, several items, which are going to be a part of your final product. So we call these children of the parent items. And there is this relationship between the children and the parents. I mean, in order to create a parent item, how many units we need from each child. These relationships are expressed in the bill of materials by using a product structure or product tree, let's just say. And we should say that the lot sizing decision of a child item is dependent on the lot sizing decision of a parent item. And the determination of optimal lot sizes simultaneously for all items become a very complex problem in that sense. So simultaneously trying to find the optimal solution for each lot sizing problem for each item. And imagine if you have an automobile to manufacture, in the bill of materials, you have thousands of children items in that product structure, in that bill of material, and trying to determine the optimal lot sizes for each of these materials is going to create a complex problem for us. So within the MRP packages, MRP software packages, they usually introduce some heuristics as to yield you alternative solutions to the lot sizing problem, and all of them can be used for different type of demand patterns and parent-child relationships in the bill of material. So we are going to start with the simplest of these heuristics, the lot for lot heuristic, in the next video. So we are going to see each other in the next video.